All right, so today we're going to talk about more arc length and radians. So in other words, it's just going to be expanding on the last lesson. We did this one in person, of course, but still the same concepts are going to be covered. Here we go. So like I said, we're going to expand on the concepts of arc length and radians from last class. We'll look again at angles on the Cartesian plane. We'll talk again about what are radians and how that relates to arc length. And then, of course, we'll look at a ton of different examples of problems involving arc length and radians. So in other words, we'll look more at some real world kind of situations where we might be actually using these. There should be a fair amount of practice time today. Let's get going. So on the following circle centered on the Cartesian plane, 4 different quadrants and all that, how can you find the measure of the angle or angles in standard position that pass through the points on the circle where x is equal to -4? So this question was kind of nice in how it was set up. It told us there's angles and there's even points, right? So it's kind of hinting to us there's going to be more than one. When x is -4, that's way over here. But you'll notice on our circle, that makes this point right here, but it also makes this point right here. Anyway, so if we're going to look at the measure of the angles in standard position of a line going through those points, we're going to have one angle that's going up this way, and then we have another angle that's going down this way. Now, keep in mind that that phrase there, standard position, means the angle in reference to where the terminal arm is, as well as its arm on the positive x-axis. So the first angle we have here will be this full angle like this, and then the other one will be this full angle like this. Now, nevertheless, despite the fact that we're dealing with those angles, it's always still important to set these up as right triangles and find your reference angles. So if I'm really careful here and I draw this as a right triangle, it'll be a right angle right there. We can actually quite reasonably set up our side lengths here and use it to find what the reference angle would be. Remember, a reference angle is between your terminal arm and the nearest x-axis. So in this case, it'd be right here. I'll call that theta r. In terms of side lengths on this right triangle, of course, we know this bottom one has a side length of 4, or more accurately, -4. In terms of my y side right here, just visually, you can say that's exactly 3. It looks quite clearly that it is going through the point +3 up there. And what we're interested in, of course, is finding theta r. So theta r, we can just use trigonometry on this one. We know we have the opposite side and the adjacent side, so we'll be using tan. Anyway, long story short, we'll say tan theta r equals opposite, which is 3, over adjacent, which is -4. Just remember, my trick with all this is never use inverse trig on a negative number. So even though there's a -4 in there, I would just pretend it's positive for a second. And then we'll deal with that in a moment. Here we go. So anyway, inverse tan of 3 over 4 to get that theta r out of there. Theta r is going to equal, we'll just say to the nearest tenth, because it doesn't say what to round to, 36.9 degrees. 36.9 degrees. Now that's a reference angle. That's not our true angle. That's just how far we are above the nearest x-axis here. But keep in mind, you can use your reference angle to find what your true principal angle would be. So since we're in quadrant number 2, this 36.9 degrees is how much we're coming off of this x-axis. And this x-axis would be 180 degrees. Since we're coming off of that and we're going down towards a smaller angle, we can just take this 180 and subtract away that reference angle that we found. So minus 36.9. Give me a second here. Oops, 180 minus 36.9. There we go. That gives me in my calculator 143.1 degrees. Awesome. So that's one of our angles in standard position that passes through the point where x is -4. However, we have this other one down here, right? We have to deal with this as well. So also set up a right triangle on that one. That was miserable. Let me try that again. Set up a right triangle on that one. This time, this side length is -3. Not that it matters when you're using inverse trig on this, of course, we just make it positive anyway. What you'll notice is it'll give you the exact same reference angle as the other one, because the side lengths, like the opposite and the adjacent, they're the same. So we'll have the exact same reference angle, but this time, because we're down in quadrant 3, we're getting an angle bigger than 180 degrees. So we need to take 180 and add 36.9 degrees to it. So 180 plus 36.9, that gives me 216.9 degrees. Awesome. So moral of the story is always draw a picture when you have questions like this. See what your reference angle would be, and then use your reference angle to find these other points. That's about all there is to those. So anyway, moving on. Arc length and radians. So remember, we did introduce this last class, a brand new kind of concept of arc length and another brand new concept of radians, which is just another way of measuring angles. So first question here is, what is the relationship between the arc length and the angle measure in radians? Well, hopefully what you remember is an angle measure in radians is just basically a way of saying how many times bigger the arc length is than the radius. So if you had an angle measure of 1 radian, that would mean your arc length is the exact same size as your radius, right? Same thing. It'd be 1 radian, 1 radius, 1 arc length, etc. Right? Long story short, just to make this even simpler, because your angle measure is how many times bigger your arc length is than your radius, we could just write that is arc length equals your angle in radians multiplied by your radius. So if you had an angle in radians of 3, that just means your arc length is 3 times what your radius is. This one, though, on the other hand, what is the relationship between arc length and degrees? That's where things get a lot more technical. It's kind of strange when you deal with arc length in terms of degrees. The way I would highly recommend you do it is if you have an angle measure in degrees, you can either turn it straight to radians, which I'll remind you how to do in a little bit here, or you can just understand that the amount of degrees that's creating your arc length is just some proportion of a full circumference of a circle. In more plain English, we can say that our arc length is just a fraction of our entire circumference. Well, the circumference is just 2 pi r. 2 pi r is a full circumference. That would be the circumference of a full circle. But your arc length is just a proportion that's going to be equal to the proportion of what your degrees are. So what I would do is I would take your degrees, I'll just say it's theta, and divide it by 360. So for example, if you had 90 degrees as your angle, well, 90 degrees out of 360, 90 out of 360 is 1/4, but 90 over 360 is just another way of putting it. It's a fraction of your whole circumference, right? So you just take your angle as a fraction of your full circumference and multiply it by that full circumference. Obviously, that's a much chunkier equation. Generally speaking, if we're looking for arc length, we don't want to have it in degrees because this is a little bit more work, but it's not the end of the world. You can still take care of it either way. Now, here's something else. We were going to do this in person, but of course, since this is an online lesson, it's not going to work. I'm just going to skip this. Next up, let's actually get a chance looking at arc length itself. So determine the arc length in this circle. Well, hopefully you notice in this circle, we are given an angle of pi over 6. That's clearly not a measure in degrees. That is actually a measure in radians. You'll find it's very common, actually, that radians are usually expressed in terms of some sort of fraction of pi. That's because a full circle, of course, is 2 pi radians. So having some fraction of pi just basically tells you what fraction of the whole circle it is. Anyway, so long story short, because we know that is in radians and we're looking for arc length, just remember that arc length is theta in radians times by your radius. So we can just say arc length equals pi over 6 times, that's a really ugly looking pi there. Hold on, I'm going to fix that. I'm going to fix that there. Hold on. There we go. Pi over 6 times your radius, which is 13. Give me a second here. I'll throw this in my calculator. It doesn't tell us what to round to, so I think it's always just safe to round to the nearest tenth. Anyway, pi over 6 times 13. This gives me an arc length of 6.8. And it looks like the units on that are inches. So 6.8 inches. That's all there is to it. So if you have an angle in radians, you're good to go on this one. Now, next one, the arc DE of a circle with a center point 0, or O, I guess is what that is 1/6 of the circumference. Determine the exact value of the size of angle DOE in radians. Okay, so this is an interesting one. It gives us an arc and they call it DE. So what that basically means is if we have some sort of a circle, DE is just an arc of that. So we can say this is point D and this is point E. And so this arc right here would be arc DE. And it has a center point of 0. So there's some angle that creates that, or I guess center point of O. I said 0 before as well, is what it is. Anyway, center point of O, we want to find what that angle is in radians. Well, since we know this is 1/6 of the full circumference, why don't we just take a full circle in radians, which is 2 pi, and we multiply that by 1/6, right? So we're just taking a full circle multiplied by 1/6. Anyway, that gives us 2 pi over 6. That simplifies though. 2 pi over 6 cleans up to pi over 3. That was all there was to that one. Okay, anyway, moving on. All right, here we go. Here's some actual like real world concept kind of things, right? Not that you'd ever do this, I guess, but who knows, maybe you would. So a windshield wiper on a car is 24 inches long. How many inches will the tip of the wiper trace out, assuming the wiper moves at a right angle? There we go. We have a right angle there. Okay, so I would assume since the windshield wiper is 24 inches long and it's pivoting on this arm here, we can assume 24 inches is basically our radius of a circle, right? So it's going out some sort of an arc at an angle of 90 degrees. Basically that windshield wiper, that arm right there, that's going to be our radius. Now, a right angle, we all would know as 90 degrees. But remember, when we're finding an arc length, which is what the wiper would trace out, when we're finding an arc length, it's much, much nicer to have it in radians already. I suppose you don't have to. If you want to use that really longer formula to calculate this using degrees, by all means. But personally, myself, I'd rather turn 90 degrees into radians and then go from there. There's a couple different ways you can go from degrees to radians. You could use that formula we introduced the other day. I'll use that one in a second. Or you can just recognize what proportion of a full circle this is and just go from there. What I mean by that is 90 degrees is a quarter of a full circle. So you could just take 2 pi and cut it into a quarter size, right? Up to you. Anyway, I'll use the conversion factor though. To convert from degrees to radians, you just take your degrees, multiply by the unit you want. Well, we want radians, so I'll say 2 pi. And divide by the unit you want to get rid of. Well, we want to get rid of degrees, so I'll divide by 360. The bottom line is, in this conversion fraction right here, the top and the bottom should be equivalents in radians and degrees. In other words, if you didn't want to use 2 pi over 360, you could have used 1 pi over 180, because those are also the same between radians and degrees. Anyway, long story short, 90 times 2 pi over 360, think of this as 90 over 1, so this makes it 180 pi over 360. Well, 180 over 360 simplifies down to 1 over 2, so this is just going to be pi over 2. That's our angle. So we have our angle now, and we have our radius. Remember, arc length is just theta times r. This gives us arc length equals pi over 2 times r, which is 24. Give me a second here. A equals pi over 2 times 24. This gives me to the nearest tenth, I guess. It doesn't say what to round to. Really, I should change that. Always round to the nearest tenth, I guess, if it doesn't say. 37.7, and the units on this are inches. 37.7 inches. That would be the basically the distance that the tip of the windshield wiper would trace out. That's all, right? Moving on. Next one, a person on a Ferris wheel moves a distance of 5 meters from position P to position Q. Okay, so someone's sitting on a Ferris wheel and they move from one position to another. I'll just call this P, and I'll call this one Q, we'll say. Doesn't really matter, I'm just picking them arbitrarily. And that distance, of course, is 5 meters. Now, if the diameter of the wheel is 18 meters, determine the measure of the central angle to the nearest tenth of a degree. Finally, I tell you what to round to here. All right, so bottom line is we were given a diameter. A diameter is the whole distance across the whole Ferris wheel. Remember, when we're dealing with arc length, we don't care about the diameter, we actually care about the radius instead. So good news is we can easily change a diameter to a radius. Radius is just half a diameter. So we'll say the radius here is 9 meters. I'll even draw that on here. Let's say that's the center there, and we'll say that's the center right there. So there's 9 meters there and 9 meters there. Basically, what we have to do is we just have to kind of go backwards. Remember, our formula is arc length equals theta times r. We know our arc length in this case is 5. We don't know what theta is, and we know r is 9. So here's what I would do. I just divide over 9 on both sides there. Now, it does say we want it in the nearest tenth of a degree. So this formula here does give it to us in radians. So long story short, we know our angle is 5 over 9, but that's 5 over 9 radians. We need to turn that into degrees. So to turn it into degrees, take your amount of radians, so 5 over 9. And yes, it's okay for it not to be based around pi. Radians can be literally any number. It's okay, right? Anyway, so take what we have in radians, multiply it by the unit you want. Well, we want degrees, so I'll multiply by 360. Divide by the unit you want to get rid of. We want to get rid of radians, so I'll divide by 2 pi. 360 and 2 pi are equivalent. That's why we can do this. Anyway, let's clean this up. 5 times 360 is 1800 over 9 times 2 pi, which is 18 pi. Actually, long story short, I was going to clean this up as a fraction. I totally forgot. We have to round to the nearest tenth of a degree. Never mind, just divide this all together. 1800 divided by 18 pi in brackets. This gives me to the nearest tenth of a degree, 31.8 degrees. That was a little bit of a sloppy way of doing it, but it works one way or another. Long story short, we want to be using that formula, A equals theta times r, and just recognize that, of course, theta has to be in radians. That's all there is to it. All right, a couple more problems here. A satellite makes one complete revolution of the Earth in 90 minutes. Assume that the orbit is circular and that the satellite is situated 280 kilometers above the equator. If the radius of the Earth is 6,400 kilometers, then find the speed of the satellite in kilometers per hour to the nearest hundredth. If you've taken physics 20 with me, you'll look at this question and go, hey, wait a minute, this looks exactly like something we did back in physics 20. You'd be right, it is very much like it. But this time around, we're not going to use physics to solve this. We'll use some math to solve this. Let me show you what I mean. Having a picture here is going to be worth 1,000 words. Let's say this is Earth, and we got the satellite. Like we'll look like this is the North Pole kind of thing. We're looking down above on this, right? If this is the Earth and this is the satellite zipping around Earth on the outside, pretend that's a perfect circle. I know it's not ideal. We know that, of course, that the radius of the Earth is 6,400 kilometers. This was not drawn to scale, but the radius would be this one, 6,400. But the satellite is situated an additional 280 kilometers above the equator. Really not drawn to scale here, but just to give you the idea. That means the full radius of this satellite's orbit is going to be the Earth's radius plus the satellite's distance above the equator. So long story short, we're going to go 6,400 plus 280. And this is going to give us 6,680 kilometers as our radius. Now, we want the speed of the satellite. The speed, of course, is basically just going to be our distance over our time. Now, that is totally physics here. But the idea is, since we now know the radius of our orbit, and we know it makes one complete revolution, so it goes an angle of 2 pi radians, we can basically find what that circumference is, and then just divide that distance that we covered by our time, which is 90 minutes. But of course, we want it kilometers per hour, so we'll need that in hours. This is totally a physics question. This is almost not even fair for math. But hey, you know what? We're going to do it anyway. So long story short, because we know our radius here, we can find what our total distance traveled would be. We can just say our arc length is theta times r. Our arc length in this case is a full circle, so we have 2 pi times r. That is just the formula for a circumference of a circle. Mwahaha, right? No big deal. Anyway, A equals 2 pi times r, which is 6,680. This gives me an arc length of, 1 second here, 2 times pi times 6,680 gives me 41,971.67785 kilometers. Now, we want to turn this distance that satellite has traveled by its time. Distance divided by time, kilometers over hours, kilometers per hour. That is going to give us our speed. Just keep in mind, we have kilometers for our distance. They give us minutes for our time, but the good news is 90 minutes, just divide that by 60 and you'll find that's 1.5 hours. So just take this distance and divide by 1.5 hours. Divide by 1.5 hours. Long story short, our speed equals, there we go. We want it to the nearest hundredth, it says. So the speed is, buckle up here, 27,981.12 kilometers per hour. That thing is absolutely clipping. Not really a big surprise if you happen to make it all the way around the Earth in just 90 minutes. Obviously, that would have to be going extremely fast, but there it is. That's our speed. Cool. Hopefully that makes some sense. We've only got a few more questions left, including a diploma one here. Sorry, I'm just jumping around. Next one here, a circle with center C and a minor arc AB measuring 15.2 centimeters is shown. I don't like how they call it a minor arc, but you get the idea. It's just this to here. The picture kind of tells you the story. Given the angle ABC right here, that's that angle in this triangle, and angle BAC, that's this one right here, are both equal to pi over 6, find the perimeter of the triangle ABC to the nearest tenth. Ooh, this is a sneaky one. This is a really, really sneaky one. My goodness, holy smokes. This actually might even be a haul back to math 20-1. Okay, interesting. Wow. So we want to find the perimeter of that triangle. I guess here's something we can do. We don't actually need math 30-1, at least I don't believe so, or 20-1 on this one. I don't believe so. Hold on, let me just double check. What I think we're going to do here is, since we know both of these are pi over 6, so we got pi over 6 here and pi over 6 here, we should theoretically be able to find this other angle right here. Well, remember back to what the angles inside of a triangle need to add up to. Inside of a triangle, angles need to add up to 180 degrees. This is the exact same as it would be in radians, of course. But just remember, in radians, 180 degrees is actually pi radians. So all three of these angles need to measure up to 1 full pi. Long story short, how about we just subtract these other two away from a full pi to find what this other missing one is here. So if we go pi minus pi over 6 and minus the other pi over 6, the leftover we get from this will be equal to that angle ACB right here, right? Anyway, hopefully you see that in order to subtract fractions, they all have to have the same denominator. Pi would just be 6 pi over 6. That would leave us, if we go 6 pi over 6 minus pi over 6 minus pi over 6, we would be left with just 4 pi over 6. Or if you prefer a cleaner fraction, that would be 2 pi over 3. Now, the reason that that is all nice is because with this angle, we can actually use the arc length formula to find this length right here and this length right here. What I mean by that is these lengths would both be radiuses of the full circle. So if we use arc length equals theta times radius, we can work our way backwards and find what that radius would be. Anyway, what we need to do is we need to just say our arc length, which is 15.2, is equal to theta, which is 2 pi over 3, times r. We need just to divide that away and get what our r would be equal to. So 15.2 divided by, in brackets, 2 pi over 3. This gives me roughly 7.26 centimeters. So we know we have 7.26 centimeters on each of those right there. Now, as for this last side length, because it does want the whole perimeter of triangle ABC, as for this side length, just off the top of my head, there's not really any way to do this using just Math 30-1 concepts. We might actually, unfortunately, have to take a bit of a callback to Math 20-1 now that I'm seeing it, right? It's interesting. I'm just kind of like going at this as I'm picking away. What I mean by that is, hopefully you remember from Math 20-1, and if you don't, that's okay. To solve the missing side lengths inside of non-right triangles, you have to use something called sine law or something else called cosine law. Sine law is the one that you'd like to use. You only have to use sine law, or rather you can use sine law if you know an opposite pair of an angle versus a side. Now, just because I don't want to totally screw these things up, I know sine law works in degrees. I'm honestly not 100% certain if it works in radians. I don't see any reason why it wouldn't, but just to be on the safer side of things, I'm going to change these into degrees before I actually switch over to sine law. In degrees, pi over 6 is actually just 30 degrees. And again, if you don't believe me that pi over 6 is just 30 degrees, you can always just go pi over 6 times 360 over 2 pi. So that would take radians and put it into degrees, and you'll see you'll get exactly that. 2 pi over 3, excuse me, 2 pi over 3 on the other hand, 2 pi over 3, I believe, is 120 degrees. So 120 degrees would be this angle just down there. Long story short, if we're going to use sine law on this one, we need to set it up with what we want on the top over what we already have. We want this angle, or this side length right here. We'll call it x. So I'll call it as x over sine of the angle across from it, so sine of 120, equals another side length that's known, which is 7.26, over sine of the angle across from it, which would be just 30 degrees. Long story short, we just need to multiply both sides by sine 120, and we would be completely done. Just make sure your calculator is set in degree mode if you're going to be doing this. If we do this, we get, 1 second here, we get about x equals 12.57. So long story short, to find the perimeter of this triangle, we just have 12.57 plus 7.26 plus another 7.26. Give me 1 second. There we go. This gives me 27.09, but it also says to the nearest tenth. So guess what? That makes it 27.1, and the units on that are centimeters. That would be our whole perimeter right there. Holy smokes, that was a tough question. That was a really tough one. There probably is another way you could have gone about doing this without actually using Math 20-1 concepts like sine law. And I'm going to be honest with you, sine law really doesn't come around much in this course. I don't even think it's an expectation for you to know it. But still, that was a good exercise one way or another. That was actually a good question just to check that we knew what we were doing. Final question of the day. This one is a diploma exam question. A dog is tied to the corner of a rectangular garage. So he's got his leash there. He's given enough leash to run a 20.0 meter circular path, completing 3/4 of a circle as shown in the diagram below. The length of the dog's leash to the nearest 1/10 of a meter is blank. I actually want you guys to pause the video here and give this one an honest try. You can see the number of students in the province that got this one right up in the top corner there. But pause the video, I'll go over it in just a second. Okay, I'm going to go over this question now. There's a couple key things to this. We're looking for the length of the dog's leash. If you imagine the length of the dog's leash here as being part of a circle, you'll see that that's actually just a radius we're looking for. We're looking for a radius. This 20 meters we're given is an arc length, so we have an arc length. You might understand that, of course, arc length is theta times r. That's the only relation that we have that connects the two of those. But it doesn't at least appear at first glance that we were given an angle, certainly not in radians. Now, the thing is, we actually kind of, in a way, were given an angle. We were told that it completes 3/4 of a circle. Well, 3/4 of a circle, we can just take 3/4 of a full circle angle and get the angle that we're actually moving at. 3/4 times a full circle, which is 2 pi, would give us 6 pi over 4. Because again, just remember that is 2 pi over 1, right? So 6 pi over 4, or if you prefer something a little cleaner, that'd be 3 pi over 2. That is going to be our angle. Long story short, to find our r, the radius of that dog's leash, well, the length of the dog's leash, which just happens to be a radius, we just have to throw those numbers into the formula. So we have 20 equals 3 pi over 2 times r. Divide by 3 pi over 2 on both sides. Here we go. Divide by 3 pi over 2 on both sides, and we get r equals, to the nearest 1/10 of a meter, 4.2 meters. So quite remarkable. 47.7% of students got this one right. It probably was just a very strange context that threw a lot of students out here, because really it's just a matter of understanding that arc length is theta times r. Anyway, that was longer than I was hoping it would be. Not a horribly long lesson by any means, but still, one way or another, for practice, we do need to do these questions here. Page 175, questions 3, 4, 8, 9, 11, 13, 14, and 16. As always, if you have any questions about any of the things we've learned, please make sure you reach out and ask for extra help.